Okay, so we share screen. We had to do two things. Sharing screen. We had to do two things. We had a microcontroller, pins, and we had to hook it to a push button and then add a capacitor in parallel for the bouncing. It's connected to ground, but not necessarily has to be connected to ground. It can be connected to VCC. The other thing we have to do is
You said capacitor has to be after the switch.
oh, sorry, yeah, sorry. It has to be in parallel with the button. Yeah, thank you, Punit.
Yeah.
And we had to hook it like something analog, like a knob or an analog sensor. Let's say it's a knob. You 3 pins here. One is for the pin, one goes to ground, one goes to VCC. I don't know if it's this ones. And we have to read here. What is here? What is here? So we have been doing this like in C, and we have to start things like, but this also can be done very easily with, I mean, for people who hasn't done anything before, similar to this, we can do it like in Arduino IDE very easily, because all of this can be like reading the state of a digital button, like a digital input, meaning it can be as simple as this line. Just as what is the button state is this command digital read the button pin, which you have declared before, and also an analog file open. An analog input. There are many examples in Arduino IDE. It can be as easy as analog read. So you don't need to go very complex if you don't want to. Like for starting, you can start with this. But it is better to have something, to have done something even in Arduino IDE, better than doing nothing. So, and this week is very important that at least two concepts of digital read and analog read are very clear, and everyone has gone through this. Because we have to design a board again, like in the week of electronics design, and then mill it, and then program it, and then read values from it. So In Arduino, if this goes like from 0 to 255, you activate, this is the 8-bit resolution, 8 bits of resolution analog to digital converter. In the Arduino, if you activate this, there is a function that is called map.
Francisco, by
Yes?
default, isn't it 10-bit or AVR?
By default in the Arduino IDE, you mean?
I don't know for AVR. I've seen only 10-bit being used. And if you want to use 8-bit, then you've got to specify it as 8-bit or something, like at least in the C. So how does Arduino IDE take care of this? 8-bit or 10-bit? How do we switch and how do we specify that?
Yeah, it's a good question. Let me go back. Oh, I didn't. I removed this, so doesn't matter. It's we need the 80 tinies
Yeah,
or what?
I think all. I'm using 44 right now. Yeah, I've gone through all this. It's in page number 148.
Sorry.
148 or something.
So where is it? It's a 10-bit ADC.
Yeah.
In here, what he's doing is in the ADC. No. Oh, 500. So we have the. Well, it's gonna take ages.
Can you try page number 150?
Page 150.
Yeah. That is where all the status registers and for ADC control is there. I think 148 or 150 from 148. And
Oh, I
channel
see
is
it now.
16. Uh,
150.
yeah, page 150. Oh. Yeah, this one. It has like 148 or something. All the status register like much 140. Yeah, this is the final register. I think you have to go much. Yeah, all these things.
Huh. Oh, it has sensing. It has a sensor temperature sensor inside.
Yeah, it has an internal temperature sensor. That is ADC 8. 8th channel.
So we take in. Let's see, we find the first ADC page. Yeah, here. Well, actually, I want to go. Yeah, to the very last pages where there are the tables. Well, is there one register? Here, there's one register where you select. I don't want to do other register page.
On the register page?
One register, you select 8-bit or 10-bit. In C or assembly. This is one register for that. That is controlling if the output is going to be 8 bits or 10 bits.
Yeah.
But I don't find this page now. It must be over here. Let me check. This. Comparator.
Here, it is belt. It's the belt, huh? I think. Did you check it? Nice. Yeah.
Compare. Timer counter.
This. So, right. Just, like, I mean, I can use it in the project. Okay. Make it more efficient.
Well, I cannot find this now.
One slide.
Yeah. How do you switch from 8-bit to 10-bit to 8-bit?
By default, it's 8-bit, right?
Huh?
By default, it is 8-bit.
No, by default it's 10-bit.
10-bit.
Yeah.
I didn't try with that 328, but it's possible. But check the data sheet.
Yes. Yeah. Is this register? If you see Neil's code here, let's say I don't know. Is this analog? Maybe. And actually digital converter.
No, it just like what?
This bit. This is right adjust.
Yeah, but that is
But if you adjust this to left, you change it to 0, becomes an 8-bit ADC.
oh, okay, that's how.
In this is where it selects 10-bit or 8-bit. It is usually doing right adjust,
Maybe you have to
but
calculate in decimal.
this register can be set to left adjust, and then it becomes an 8-bit.
Okay, okay, fine.
So you look for this
Yeah,
bit
yeah,
in the register, in this register.
yeah. Okay, got it.
Set
But
it to
how
left.
does Arduino IDE take care of that? It is by default 8-bit, and
Is by default the 8-bit?
in Arduino, is it?
I don't think so.
Like
Let me check in this Arduino code.
Yeah, just a second.
I think it's 10-bit.
it's better to time. Precision will be
Precision will be better, I know, but it will be faster with 8-bit. So we are discussing how to switch from 8-bit to 10-bit and vice versa. And what's set by default?
the smallest chip. It was like 8 bit, yeah, 256. Smallest chip by default.
This analog input,
Yeah.
oh, it doesn't tell.
That's an if condition.
But I think it's in.
Does not. Yeah, I felt it and I feel like that.
Same arpeggio.
Okay, we'll find.
Nowhere here
Yeah,
declare 8-bit or 10-bit.
yeah, I'm sure we'll find out about that later.
Should be something in declare here in the setup. Be one comment about this. By default is getting the maximum one, which is 10-bit, because
Yeah, I'm sure there will be some note on that. We go to Arduino.
yeah. Then for the people who doesn't want to mess with all of this, you don't have to write all of this. Like beginners, you don't have to not even understand all of this. You can go with, well, again, is it close?
Huh?
Oh. Close again. No, I didn't close it. Yes. You don't need to do all of this. You just in here. You just have to read this. I'm talking this for people who doesn't know all of this, and they get stuck, and they don't move forward. You have to move forward. So if you feel this is like very complicated for you now, just stick to Arduino IDE, and then after you get the value, you get this number. Okay, you have you have to obtain here your number from this range here, or from 10-bit. You have to obtain like this other range. Then there is a command called map. This command is in Arduino. This command, you have to do the math manually if you want to go in C, or if you want to go in C or assembly. So this map command convert these numbers onto whatever you want. Like say you have in the datasheet of your sensor this graph. That relates 0 volts, 5 volts to say 20%, 80% of humidity. You look for this in the datasheet. So you see that 20% is 1 volt and 80% is 4 volts. And important, this is linear. Okay. So first, you have to map. 1023 to 5 volts, and then map 5 volts. No, then you map the following. Or you can do it. Yeah, you can do it manually. You map 1 to 5 to 4 volts. You map it to 20, 80%. So the goal is that you map. Let's go to do it straight away. Sorry, delete what I said. You have to do this map. You have to tell in 0. Let's do it right. Forget what I said. This is for doing manually, but for doing it in the Arduino, you have to map. You have to get this graph, and you got to get the value at 0 volts and at 5 volts. And say at 0 volts. Sorry, confusing you. Say the value of this sensor at 0 volts is, I don't know, 20%, and this is 80%. So you have to map this to 20, 80. And the Arduino will convert any value in this range to any value in this range after the map. It's a little bit confusing to explain it like this.
I think everybody is electronic engineer here, so they will understand. Sure.
Map.
Electronic engineers at least will understand it easily.
What is this function?
Well, you don't have to explain too much, I think, because a lot of us are fresh graduates and engineers, so this must be a not that great effort for us.
Okay, it's an easy command, but you need this for getting the. We don't want like the number. We want the value of the sensor, and for this you have to go to the datasheet. The map is clear. The problem is when this when all of these sensors, if they have a linear behavior, you can get straight away one voltage and relate 1 voltage to the value of the sensor. The problem is when this sensor is not linear. So if it's linear in like this, you have to divide the sensor in two and do one here and one here, like two maps. You understand? You have to do two sections because the behavior is not linear. It's only linear in this chunk and in this chunk. And worse than that, is it clear? What's
Non-linear,
here?
right? Exponential or parabolic or whatever kind of curve.
And finally, if the sensor is like this, you cannot. There's not any sense to read it in analog, or you have to make a function. You have to build your own function that you approximate this in linear stages for every given. So these are more complex. We are not doing this now, but take into account that if you are doing something that is not linear, you cannot do what we are doing now. You have to divide the values of the sensor in small chunks. Okay. But usually what happens if you have something like this or even more complex, like if the sensor is doing like this, very complex function, and you don't want to miss like this because maybe you go from here to here linear and you miss this peak, and maybe this peak is important. So what usually happens is when this happens, they don't deliver an analog output. What they do is they just feed you the data. So the sensor internally has its own microcontroller that is doing this, converting these analog values internally to the data and is feeding you the data straight away. So you have to care about all of this.
So that is I square to I square C protocol.
Yeah. There are many protocols, can be serial, can be I2C.
SPI.
This, we will be doing this in networking, in the networking week.
Okay.
Okay. It's a special case of input devices, which are actually, they are just network. So you have to set things like this. So
More more importantly, should we discuss about voltage dividers?
voltage dividers?
Yeah, setting the range for the sensor for the ADC to capture. Is that important?
Sorry again.
Voltage dividers. You want to set a range for the sensor. For the ADC to read the values from the sensor. So usually, like the sensor might give 0 to 5 volts, but you can adjust the voltage so that you read from some volt to some volts. It says ADC is very sensitive to what do you say, the voltage. It can go up to has a tolerance of plus 0.5 volts and minus 1 volt. So from minus 1 volt to plus 5 volts, VCC plus 5 volts, it can measure, and above this, it doesn't work properly.
Yeah. What discard? We have been talking here about detecting from 0 to 5 volts. Okay, what Puneet is saying is that the sensors, let me see if I got your question clear, that usually sensors, they don't go from 0 to 5 volts, they go from 2 to 2.5 volts only. Say something like this. So you only have 0.5 volts here, and you want to transform this into something bigger.
No, no, I was
Something like
just
this that you're talking about?
no, I wasn't saying this. It says like I have read in the data sheet or somewhere that the ADC when it takes the voltage, it is very sensitive to voltage. It can measure measuring range is -1 volt to plus VCC, that is 5 volts plus zero point 0.5 volts. So if you give a voltage greater than this to it, it might damage the ADC, uh, and you have to keep the like whatever sensor reading you get, you have to keep it in the range of -1 volts to VCC plus zero point 0.5 volts
So this is, you meaning this is
range of the ADC.
the danger area?
After
I
this,
think.
above this, like below 1 volt, -1 volts, and above 5.5 volts is a danger area. And this is the range
And
ADC
we are
can actually
we
measure.
are using based on our own BCC, so they are delivering in this range, usually in these smaller ranges.
Yeah, so we have to set the ranges and all.
Yeah, the thing is about this, what you were saying. I mean, for me, I haven't seen any sensor delivering 6 volts or something like this.
Yeah.
If this is the case, I think in the datasheet they should be uh, how to do a voltage divider, like to get this down.
Yeah, I'll
But the
probably
usual problem we have is the opposite.
yeah.
The usual problem we have is that the analog sensor is only giving this range of resolution. So all happens in a very, in 10 times smaller than this. So usually we have two options here. You can use this and then you have 10 times less resolution, or inside the data sheet there are usually a small electronic diagram on how to convert this into a bigger range, so you can read it better with better resolution. Usually all of this is in the datasheet, how to do this. But let's see case by case. If you find something, like for example, I remember this sensor. Let me check the magnetic field. Where is the datasheet here? This is an analog sensor. So here is giving you the data sensitivity, the voltage you have to supply to this. Power on time, sensitivity with temperature, if you want to do the math. It has drift. Drift is very important property you have to take into account. Symmetry, sensitivity, radiometry. So yeah, it gives you all about temperature. Yeah, it gives you a mini circuit that what is the usual application. And here it tells you, you see, voltage out. This is where you have to hook it to the to your microcontroller. But what I am looking for is for the range. So look, it has 5 millivolts per Gauss. So here now we are under 500 Gauss. Okay. So this is the sensor that goes to 0 or 1000, about this range when you flip it up or down. So it detects the. Oh, sorry, with the magnet. I mean, with the magnet you can go 0 or 1000, about this with a neodymium magnet. So I don't see the graph here, but in here there is the graph that tells you what is the output voltage. It is centered in in 2.4. No, let me say D out here. Electrical magnetic sensitivity. Okay. D out is 2.5 volts.
Minimum is 2.4, maximum is 2.5.
This is with the magnetic field of Earth only. And then it's incrementing with 2 or 5 or 1 or 3.1, like all of this, depending on the model you have, millivolts per Gauss. So this is where you have to do the math. And here in the video he's showing and he has a JavaScript version. This is a neodymium magnet. Goes to 0. So if you check when it's far from, it's like 500 Gauss. And if you flip it, goes to near 1000. So if you have applications with magnets and you want to trigger things, one place to look into this is super magnet. These are magnet suppliers. Okay. And in here, like you can check one, say one of these, like this one. I'm sure you have places like this in India, but what I want you to check when you look into a magnet is this value, N45. This is how strong it is, and also the physical properties of the magnet, because with this magnetization and the physical properties, you go to a magnet calculator. You select the grade of the magnet, the thickness, and very important, the distance. Like my sensor will be 2 millimeters or 10 millimeters from this, and you can have among these forces, but this is what you want to see. How many Gauss will you have at this distance? So with this Gauss, you have to prepare your sensor to read from these values. Okay. If you want to trigger something, you need to do all of these things. This I have done with the magnet, but there, with every sensor, you will find something similar to this. You have to go from physical properties of your setting to something you can read. In this case, this is the minimum it will go, 380 Gauss. So you can trigger, if you set your trigger to say something out of this range, it will not read, the value, your trigger. But well, who did any of this at all we have been talking about here? This.
I tried to do, not succeeded. I did the debouncing. I have a different strategy for checking the the bouncing nature of the switch, which I'm yet to document. But that I found in AVR programming book, how to check the bouncing. So I haven't done it with the oscilloscope. Yeah, so I did the bouncing. I'm trying the ADC reading value using C currently.
Yeah. What about the analog?
Yeah, analog. I mean analog ADC.
What
I
is
mean,
that?
I'm doing it currently in progress.
Okay. And the rest, did all the people there choose analog device
I'm sorry.
to read? Anyone there, did they read? Did they choose an analog device? What to?
Yogi, I think Yogi is already making some stuff.
And Kavita?
So not yet. I've managed to test a button. I managed to do the first exercise that you had asked us for the debouncing with the oscilloscope. So I tested a through-hole component because the board wasn't programmed. So I tested that. I saw debouncing work. I mean, I first simulated bouncing, and then I looked at debouncing. And I'm still trying to figure out, what analog input to test. I mean, is it possible that we can use something that's not, in the Fab Lab repository, like just to understand the principle better?
Yes, it is possible.
Okay.
I mean, this is resources that you have there
Yeah.
if you want, but you can use anything, any other analog, whatever you want.
Okay. Because I was thinking of using an LDR component.
Yeah, LDR is a common sensor that many people uses to understand that.
Yeah.
But
Just
remember, it's not that easy like as hooking it and you have to put some resistors.
Yes, yes, I know. Yeah,
Like Punit said, a voltage divider, I think.
yeah, yeah, I think so. A voltage divider, yes. I
Yeah,
have to look at the
because
circuit. Yeah,
the voltage it supplies is bigger than the range.
yes.
So yeah, you can start with the voltage with the LDR. It's a very interesting.
And I was also thinking of trying a temperature and humidity sensor. I believe that is
The,
analog.
yes, there is an analog one. Yes, this encapsulated. Yes, yes, yes.
Yes.
You can use that. But what are you going to use for software?
Um, to be honest, I'm more comfortable with Arduino IDE. So initially, just to get started, I'm planning to use the Arduino IDE.
Yeah, take
Program
into
there.
account
Mm.
that say 90% of the people they are going to use Arduino IDE.
Yes.
I mean, we are talking here more in C and all of this assembly because Arduino IDE is very common and is very easy. Like doing this assignment in Arduino IDE, the most significant problem is going to be milling the board.
Yes, exactly.
But when you are comfortable with this, you will want to go deeper, to control a little bit deeper. If it's going to be 8 bits, 10 bits, like we said here in Arduino IDE, there is no easy way or known way to control this.
Yeah.
Maybe there is no way,
Yeah.
Punit, maybe there is no way. Because Arduino IDE, you cannot control all the hardware.
Yep. True.
That is why it's supposed to be easy, because you cannot control all of these things. You just leave the microcontroller to do that. Why the Arduino IDE I think is gonna think that you don't need 10-bit resolution. I mean, I think he will say you have 10-bit resolution and that's it.
Yeah, that's quite possible.
Well, maybe not, but I think you cannot change that in the Arduino IDE. But I cannot imagine some application that you don't want the 10-bit. You only want 8-bit in
It says
Arduino IDE.
it says 8-bit conversion is faster. The ADC will be much faster. Um, but yeah, it'll lose resolution.
Yeah. Then I'm gonna remove this is
Can you talk
the
about the
mapping,
pre-scaling?
the pre-scaling.
Yeah, like there are different options of pre-scaling. When do you use what? Usually, I saw like most of the codes which Neil has, at least the temperature. Uh, he used pre-scale of 128. That means the clock will be divided by 128 or ADC.
Could be.
Yeah, so why does he use that? And then if we use a different pre-scaling, what will be the result? It is recommended, it seems, for ADC to have a pre-scaling. It can't, take faster cycles. But I didn't get the logic exactly. So, like, what are the limits of pre-scalings?
Actually, I don't know. He's using a pre-scaler, yes, in the analog to digital converter. But I think it's only for not measuring so continuously, like at every cycle, because he doesn't want to read at every single cycle. Thing is for that. But why do you ask? Because he's doing different prescaling.
No, he is using a standard prescaling, 128. I haven't seen much, but the temperature sensor, he used a prescaling of 128. And most people, most of the times, like all the codes I saw online, they use a prescaling of 128.
Hmm.
I was just wondering, like, what's with the prescale?
I don't actually know very well this. We'll look into this.
Yeah. Yeah. So about the assignment, he says add a sensor to a board which you have. So we got to design a board, or we got to. Yeah, is that it? Like, is that our assignment?
Sorry again, Puneet?
What's the assignment for this week? We have to make an 80 45 and then add a sensor to it and then read it. Is that what we got to circuit, or we got to we can make any one of these, or we have to redesign it? What is it?
Yeah, the assignment for this week is you have to, a microcontroller can be an Arduino. I mean, when I say Arduino, sorry, I want to say an Atmega 328 can be
You spoiled me, Frank.
yeah, 80 tiny, whatever microcontroller. 80 tiny is simpler. I mean, 8010 45 is even simpler. You get this and you make the same design you did in electronics design, the same thing. So you start with the hello. You always start with the hello world. You don't start never from scratch.
Okay.
Where was it? Input devices. Where was the hello world?
It was in the electronics design.
Yeah, but it.
Yeah, that is the one. Echo Hello World.
You start from this board. Always. If you want, you can remove this. If you don't want it. But this is the basic board that you always start with. So with this board, you have to hook here somewhere, like the same way we did in electronics design.
Right. We can
You
add a
hook,
sensor.
yeah, you hook it a digital or analog sensor.
I don't think we can do away with the resonator.
Sorry. Oh, sorry. And then you read data from it.
Yeah. So, but I don't think we can do away with the resonator. It's important for the serial communication, right?
Yeah, but maybe you don't need serial communication. Reading data from the sensor doesn't necessarily mean that you send data over serial, because you can remove this serial communication and remove this resonator and just trigger something like an LED.
No.
You know, it's a proximity sensor that you only have to show
Right.
the, you have to read the data and do something, but no need to send this value from serial. It's good that sending this data so you can see it, but no need. But yes, let's say we want to send the data to serial, and we always hook this resonator here. With this is the basic starting point. All the Fabacdemy, we can start with this design. So if you, I always start from, because I'm using this cat, I always using this file. But if you did it in Eagle, you can start from one made in Eagle if you don't make your own, or start from whatever student from past years get his design in Eagle, or you find it in KiCad, whatever you are using. You can find the basic design here, and start from here.
Right.
Some other people, maybe they are going more advanced with the X megas, but these are more complex. If you want to try, these are very powerful microcontrollers. Now, you need the ICE programmers that you have. You can try the X megas if you want.
Xmega, you program it with the ICE initially.
Yeah, you need the ICE.
Yeah, for burning bootloader, and then after that we can use an ISP or FTDI.
If you burn a bootloader, but normally no.
I'm sorry, I didn't get that.
I mean, I don't know. I'm sure there will be bootloaders, but usually you program the always.
With
The bootloader is a program you get into here, and you also set the fuse, one of the fuses high, one fuse what is actually allowed to self-program. So you can, the next time you can enter the program through serial. But this program, the bootloader, is already taking some space of the microcontroller. It's only like for entering the program through serial instead of through the ISP. But I think only if you have Arduino IDE, you want to do that. Only if you want to do Arduino IDE.
no.
Usually we use this straight away. Put the program in here.
So FabISP
What?
also can't program this, is it?
Yeah. No, I mean the FabISP no, but the ISP connector.
Okay.
You use the Atmel ICE instead of the FabISP.
Okay. Okay. Got that.
But the bootloader is only for entering. It's something that the Arduino guys made it for make it more easy to program, like only having it through USB. So otherwise you have to hook this cable, and they are not hooking even this cable. They have a chip here to convert this to USB. So you program through the USB. This is for making it more easy for new people. It's the only thing. But no need a bootloader at all for what we are doing. So now what we have to do now is what you said. We have to do this microcontroller and hook a sensor and read some value from it. Okay, I leave you for this for tomorrow maximum, because this is what we need to do. And now we are going to talk about step response sensors.
Yeah.
Very different now.
Yeah.
Okay, so step response. Very complex matter. Discard. So what happens here when you have a button? When you have a button, push button, and you press the button, it goes like this. So 0 volts, 5 volts, whatever, it goes like this. It's a clear as a digital. because it's or this. But then with the step response sensor, you will have something that you can fabricate. Can be a piece of copper, can be something that you are going to hook it to the microcontroller, and the response that is going to, I mean, this is going to be that one. This is going to be like a capacitor. So what you are doing to convert this into a sensor, you are going to charge and discharge this thing. So when no one is touching this, it is probably charging like this and discharging like this, okay? It takes some time for charging and discharging, okay? And you, when you are doing this sensor, one thing you have to be clear when you are doing one of these step response sensors is that there is nothing derived. All the things you have to derive. First of all, this is like very complex things. You don't need to do this for this assignment. This is like advanced, okay? So if you feel that this is very complex, it is very complex. So don't worry. So you will make a circuit, something like this, that you will attach a piece of copper or something you have designed to a microcontroller through a resistor. And then the theory behind this is that you will have some status, like that you want to measure. Like say you want to measure a button press. So you have to, this is your finger, okay? This, it will be sensed by this and it will charge differently. Okay, when you approach your finger here, this, you will couple with this, with your electromagnetic field, and these times will change, be different. Okay, maybe I'm saying this the opposite now. It will charge quicker and discharge quicker. So what you have to do here is that you will have a status where you like your idle status, and you will measure this time, and you have to measure. Then you put your finger close, and you measure these times, and you obtain T2. Okay, I'm going to do it solely in the charging, or get this charging. And then if you are even touching, not even close, but touching now, you will measure another time, T3, for this to charge. And then with these values of time, you have to create a program that says you are touching the step response sensor, if it is a touch one. Understand? It's only you because these times are gonna change with many factors. They are gonna change with humidity, they are gonna change with temperature, they are gonna change with the shape, they are gonna change with the electronic fields that are around you, with the environment. So these times you always have to calculate yourself. There is no table to look at, and you will say, okay, if this time is 3 milliseconds, then I am touching the microcontroller. I'm touching this board. No, you have to calculate this. There is like a research part that you get these times, and then after that you do your program to set the triggers. And even that you do all of this, it's not guaranteed that it's going to work. Okay, because if you look at for example, what let's say Peter Boombox did for the for his final project, Matthew Kitter, the one who invented Cocopelli and antimony, he did this boombox with, you see these buttons here, play, volume, plus. These are not buttons at all. These are actually copper, and this is the board he made. It's not shown here. Behind this, there are copper pieces of copper, tin foil. So he's detecting when the finger is near this. And actually, because there are many buttons here, with this arrangement, it's different that if you have these 5 buttons here or in separate. So actually, he couldn't make it work properly at all in the end. Because as I said, it's very, very complex. Even for him that he is like an advanced user, doing things like this are very complex. So for you to understand this, I would just do a single, for now, a single capacitor. Get the mill this board, like Neil's board.
Step response.
Yeah, the step response, but not the only this one, eh? This one, the loading. The transmit receive is even more complex. So you mill this board and stuff this board. It's only based on this one resistor. This is the sensor, this one resistor, because the capacitor you are going to hook it here. So in here, what you are going to do is you are going to in the sense pin, you hook it something, whatever you want. Okay, and this is going to, whatever you hook it here is going to be charged through the PV3 pin, and this is what you are going to measure. You are going to measure this time. Neil is taking one approach that is actually measuring. It triggers here. What Neil is doing is not what you usually do. Okay, I'll tell you what Neil is doing. Neil is doing this. Neil is triggering the charge, starting to charge, so it opens PV3, so it's starting charging the capacitor. The capacitor is the thing you are touching. Then it says this is my 0 time. It's starting charging, and it wait is for 1, 2, and 3 times. See, at 3 different times he's measuring that, and this times is 1 milliseconds, this is 10 milliseconds, and this is 100 milliseconds. Okay? You only need one of these to get it. But he's using these 3 times. What happens is you understand that, eh? Okay. So say if the charging parameter is like this, if you trigger it here and you measure here, you are missing this. You don't see how fast is this. Okay. What he wants to do is, if he can measure this slope, you can actually know when you are reaching 5 volts. Sorry, 5 volts, and you can count what is the charging time. Okay. You are not understanding. Okay.
No, I got it. Got it.
Let me explain it clear.
There must be an equation to get the charging time.
Yeah, but he's not doing that. He's not doing that either. He's doing different thing. He's doing. I trigger here. I start charging here, and it starts charging, and I say, oh, forget the 3 times he's measuring because he always do it a lot of things.
Yeah.
Say it is the 10 milliseconds mark. So you decide you are going to measure only 10 milliseconds. Okay. So he's reading the voltage at 10 milliseconds, and say it is 3 volts. Okay.
Yeah, so
this is what he's doing. At 10 milliseconds, he reads the voltage. So when your finger is not there, you get 1 voltage. So you get this with no 1. You get 2.5 volts with the finger at 1 centimeter. You get 1 volt with the finger touch, and you get 0.5 with 2 fingers. He's doing something like this. Okay, he's always measuring this, and this you have to do. This is your task. If you mill Niels board and you put anything to copper, this is what you are going to obtain, values like this. But this is what the meaningful part you have to do. Okay? In Niels board, you have to do this. What is 1 finger? What is 2 fingers? What is like, for example, if you are doing the other circuit that Neil has, this other one, the transmit receive, okay. In this case, there are 2. Let me check. There is 2. There is 1 transmit and 1 receive sensors. Okay, in this case. So in this case, you will have to again clear. All of this, what I'm saying now, only do it if you are done with your assignment, okay? Because for the following week in composites can be finished in 1 day, so we can move forward and do more
molding and
input
casting.
devices.
Molding
And casting.
Yeah.
Okay. Even so, it's the same.
Yeah.
We can do molding and casting in 1 day, and keep advancing with these input devices, which is very important. So when you have two of these sensors hooked to the microcontroller, okay, what Neil is doing, why is he putting two sensors? Because then you can put here,
Copper.
no, this is like something filled with water. For example, you put this copper, you put this in the recipient, in the bottle, for example. This copper, you attach this copper to the bottle, and when you add water, you will see, you will obtain 3 volts with half the bottle. You will find 3.1 with this level, 3.2 with this level, 3.3 with this level. All of this you have to do, because for every application you are going to find, the board is going to be the same always, but depending on the electrodes you hook it, how are they made. Like, imagine, like he said, you are attaching this tape now for 2 moving parts, like this. Okay? If you move this forward and backward, you are going to obtain different voltage here as well. And this you have to say, when this is voltage, this is the physical result. You have to do this research, so later you can do the opposite. From the physical part, sorry, you will read something and you will derive what is the physical configuration. So you can make a linear sensor here, or you can make a rotary encoder. You can make something with a piece of copper and another piece of copper with different shapes, say something like this, on top. When you rotate this copper, say, make it clearer, you have this piece of copper and this piece of copper, one on top of the other, and you are rotating this one, this will also change the response. And you have to derive how many degrees relate to these voltages here. So if you want to look into this, I would start with the single one, okay? And say you do the following. You start with nil board, you mill nil board, that's it, and you just modify it so you make 2 buttons, okay? Not the transmit receive, but 2 times the nil board. And say you put under a piece of acrylic, you put 2. Let me draw this again. Under a piece of acrylic, so you cut or you get some piece of acrylic spare, and you underneath of this you put these copper things and you solder wires to this, and you experiment putting your finger on top of this, and also set a threshold so when you are near this it detects that you are touching. It's similar to what you did yesterday, Punit. Remember that you tried to do an analog sensor with a digital button?
Yeah, yeah.
So this is the same. This is the same principle. You will set a threshold that when your finger is here, you already know what is the value. So if when you press, if when you are, say when your finger is here, say this is the finger here, the value is this, you have to set a trigger like this. Okay. So when your finger gets close, you detect a touch. But this is what, like I said, what Neil is doing. If you look in the book, if you look in the book, okay,
Input.
no, in the part 2 of the book, okay, there is this capacitive sensor section that I want you to read if you want to go into this. And they are using a different approach. Okay?
Okay.
They are using this approach. They are doing this. Okay. So I trigger the counter. So I wait like say 500 or 100 milliseconds. And in this time, how many times can I charge and discharge and charge and discharge and charge and discharge and charge and discharge this thing I'm doing? And you will get a number like 500 times. And when you put your finger, maybe it's 2,000 times. Okay, because you can do it faster. You can charge and discharge it faster because your finger is coupling with this. So this is the approach you are using. It's not actually measuring this rise time, but doing setting, okay, in a fixed time like 100 milliseconds or whatever, fixed time I decide to do it, how many times I'm charging and discharging this. This is the approach they are using. I think it's a more clever approach, this one, than the one that Neil is using. Because this you have more precise. Because since you are doing this many times, you can average. Neil is doing a single measure.
Yeah.
It's measuring one measure many times, but it's measuring one measure only. Okay, so read this chapter. Because they are using a different approach here, and they are using interrupts for doing this. They are using interrupts. So when this is charged, they trigger an interrupt. This is charged. So this is doing in an automate way, doing interrupts. So this is also a good way to know how the interrupts go, like the external interrupts. Not the internal interrupts, but the external interrupts.
The internal interrupt means for some interval.
Okay. So now let me go back again for you. No one connected today.
Kochi did.
Kochi was going to be there.
A while ago.
Who's the one next to you?
Yadu.
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 Shaz.
So let me remove the screen sharing. So now, Puneet, why are you not using the other camera is
It
broken.
no. So, yeah, some loose connection. Sometimes it works, sometimes it doesn't.
How long is the cable?
From what I think it is like some 5 meters.
5 meters. Maybe it's too long.
Too long. It is it's we hacked it actually. We hacked the Ethernet cable. We connected the USB pins on either side, and that's how we are connecting. Actually, we also bought a USB cable which is long enough, and that didn't work out properly. But this Ethernet cable is working out good.
Okay, but it's not working good. It's working good, but it's not working good.
Yeah, that is because of maybe we should solder it. We have just twisted wires and all.
But not solder it to the camera.
Not the camera. We have the USB connectors which goes to the camera USB. We made an USB extension cable with the connectors.
Okay, so try to have this working. Now I'm worried about this week because this week is very important. This is like let's say this is like a pass-fail week. If you fail to do this week, you are probably not going to make the final project. More than probably. The people who fail to succeed in this week, they will probably fail in the final project because it's a very important concept to understand, digital and analog inputs. Like if you are done with your assignment, you can go through the step response because there is a lot to go deeper in that. But otherwise, just focus in the in that analog or digital sensor. So what I want you to put it now to publish to the group is I want all the people to start again with the Hello World design board. Choose a device, analog or digital, and start designing it and mill it today. And if you are done with that, then go to the step response. Read the chapter in the book about capacitance. Analyze the nil, what is nil doing. Understand that nil is measuring straight away each cycle, and the book is not doing that. The book is measuring how many cycles in a fixed time. It is doing that. And make your own sensor and obtain like meaningful readings from that.
Okay, I got it.
Okay, so this is it for today. I don't know how many people, probably no one.
Vigyan Ashram had some issue connecting, some connectivity issue. Kochi joined a while ago. Dropped down.
So one thing about the machine, who is presenting? Are you presenting the machine this today?
No, probably next week.
We have time.
Next week
I mean,
for molding and casting.
so can we present next week? Or we should this week?
Next week. This week we don't have time to do it.
Means there are many like we should.
No,
send us
no,
a-
no. But
Yeah,
we have to
present
sign
it.
it up. We have to sign up probably quickly, or else Neil will start asking.
Okay, perfect.
Yeah, you can sign up at like live. And remember, you don't have many time. You have like the slide and the video, no more than this.
Yes.
Now, it's not like the other day the people were talking like for 10 minutes.
Yeah. I know.
Now they are going to spend like very, 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 very little time. Not going to be like the other day. So I wonder why you don't have the machine yet.
We don't have people here making team. I was the only one this week, all the week. Kavita is there. Yadu had gone, and then these Nadeem and the gang had gone. So I was the only one here.
So you have to derive conclusions. I want you to derive conclusions from this. Like this is not only about the assignment, like doing the assignment, but also you taking conclusions. How do you feel like working in groups versus working individually? When you divide the task and you tell someone you have to make this task, and you go back. So this is what I want you to express also in your documentation.
Yeah.
It's not only this is our machine, but also how was
learning.
it?
Yeah, my learning about this, about the working in a group. Yeah.
Yes. Well, I mean, everyone should express their opinion of working in groups. Like everyone will have different opinions. The people that is good at working in groups, but also as leading a group is a different experience than having a single task.
Yeah.
So all of this you have to express, because in my case when I did the Fabacdemy it didn't work. For me, doing the group assignment it didn't work. We were 15 people, like supposedly everyone who is the better, like civil engineers, electromechanical engineers, whatever engineer, architects, designers, whatever. We couldn't even make a single machine that was already done. We only had to assemble it. Not even that. So please take your conclusions on that also.
Yeah.
Okay. So see you tomorrow, and let me look at this pre-scaler, because it's also something that I thought it was about what is the frequency of the measures, but I'm not sure now if it's like this. I'll
Okay.
take a look into this. We talk tomorrow. Okay. See you.
Bye bye.
Bye.